All right, so before I start, I said I would do two things. I would bring a list of questions for us to look at, as well as ask you guys if you had any specific questions. So I'm willing to start off with a question from you guys. So these are going to be basically review type questions for the exam. The list of questions is already in the shared directory, so anything we don't do today, you'll have a chance to work through yourself. And I think there'll be a lot that we don't do today. I don't feel like just doing questions for an hour and 20 minutes. So I'll leave a lot for you. So any questions for me? Okay, so I'll start off then. So in this file, it's just a plain text file. You will find a bunch of questions that are like the questions on the exam, but they're not multiple choice. And doing these questions, you can think of as good preparation for the exam. Starts out with the basics, and it's roughly the same order that this type of stuff will be covered on the exam. Starts out with the basics, basically just to see that you can read and understand Python code and know what it does. It gets into some recursion, then a little bit of questions about a little more advanced understanding Python questions, object-oriented hierarchy to look at and answer some questions about, and then some efficiency stuff. So different ways of using sets, analysis of some basic pieces of code, analysis of things like different implementations of binary search, and coming up with solutions for different types of problems. And then finally some real deep analysis of some, I won't say deep, but some analysis of some more complicated functions, including recursive ones. And what's not here, and I'll just put it on so that when you're studying you don't forget that this is still on the exam, which is basically the equivalences and differences between Python and Java. So I really left these out sort of on purpose because you've just been programming in Java for 2 assignments. So if there's anything you don't need a review on, it's that. And if you've done the assignments, then I think you know pretty much all you need to know to answer perhaps all but one of the Java questions. Yeah.
Did you give the answers to the test questions? Or
the test questions, which no answers provided. You have today's the 6th, so you have 13 days before the exam. Find some time to work on these, and if you have problems with any of them, post a message on the forum. So the problem with giving answers, there's 2 issues. One is that if I give answers, you won't think about them. And the other is they're not really necessary. For a lot of these questions, not all of them, the answer can be obtained just by typing some Python code into a Python interpreter and running it. So the first part, for example, is all questions about what does this code do? Well, if you run it, you'll know what it does. But of course, during the exam, you can't run code. You have to read it and understand it. Okay, so let's start at the beginning here. What does this evaluate to? 1 divided by 2 times 3. Yeah. So 3 over 2, or 1.5, right? Division and multiplication have the same order of precedence, so these just get done in order. This gives you a half, or 0.5, and then 0.5 times 3 is 1.5. Okay.
So we're assuming from future import division?
Yeah, I think that's even written at the top of the exam. or minus q nu if you prefer. 2 modulo 6. 2. It's the remainder when you take 2 and divide it by 6. So 2 divided by 6 gives you 0 with a remainder of 2. Another related one, let's say 8 divided by 8 modulo 6. What's that? Yeah, so 8 divided by 6 is 1 with a remainder of 2. 3 plus 4 is less than 3511 mod 7. Good. So how did you know that so quickly? Did you compute 3511 mod 7?
Yes, actually.
Yeah.
3,511 mod 7 can never be larger than 7. Like 7 and 0. So
Yeah.
it's greater than 7.
Yeah. So the answer, I don't know what it is, to this expression is between 0 and 6, and 3 plus 4 is 7. So 7 is bigger than 6, so it's not less than. Okay, so look at this expression x plus y. If x plus y are both ints, then what does that evaluate to? An int. What if x is an int and y is a float? You get a float. What if x is a string and y is a string? Yeah. And what if x is a string and y is an int? It's an error. Won't let you do it. And if x is an int and y is a string, it's also an error. X times y. If x and y are both ints, you get an int. X is an int, y is a float. Float. X is a string and y is a string. Error. X is an array and y is an int. Yeah.
We'll give an array x or y times.
Yeah. So we'll give the array x appended to itself y times, right? Because it's the natural generalization. If you say that when you add two arrays together, you get an array that's the concatenation of those two things. If I take an array and multiply it by 2, for example, so x times 2 is like x plus x. X times 3 is like x plus x plus x. And so if you multiply an array by an int, you get another array, which is that initial array appended to itself that many times. And now what if x is a string and y is an int? You get x, y times. So arrays and strings are very, very similar. They're both sequences, and they basically get treated the same way. So if I take a string and multiply it by an int, I get a string. Right. Okay. So here's some code. Function. And what happens if I call this? I call this function with the arguments the string Pat, the string Morin, and the integer 2019. $20.19. Is that right? It's 20.19. Right, so a few little things to watch for. The first and last name get reversed, and the total gets divided by 100. So really, this is the amount in cents, which is the kind of thing that cash registers do. And then the other ones like this you can figure out. Here's some little function. What happens if I call it with the argument 6.25? Six comma 0. No. So let's look at this second thing here. Feet is 6.25. 6.25 mod 1.
So you get 0.25 and then times 4, or wait, times 12.
Yeah. So remember this mod operator, it leaves you whatever's left over after you do division. So 6.25 divided by 1 is 6 with a remainder of 0.25. So this becomes 0.25 times 12 is 3. So the answer here is 6 comma 3. Okay. And I'll leave the other 3 like that for you guys to figure out. What's that? It might be 3.0, we'll say, yeah. 6 3.0, or the float 3, whatever that is. Okay, so here's 3 implementations of the factorial function. So first of all, what can you tell me about their running times? So what's the running time of, let's say, this is probably the easiest one to analyze. So if I give it the argument n, what's the running time look like? O of n. Now, this version here, what's its running time? It's O of n. It's basically, it's almost the same thing as this code here. So this reduce function is just a shorthand for walking through an array and taking, taking each element and applying this function. In this case, the function is multiplication with a running sum. So you start with the first value of the array, and then you multiply it by the second, and you take that result and you multiply it by the third, and you take that result and multiply it by the fourth. But it's still walking through the array and doing all this stuff. So that's O of n. And how about this recursive one up here? So nothing magical here. If I call this factorial of n, then that calls factorial of n minus 1, which calls factorial of n minus 2 and n minus 3 and so on down to 0. So that executes, that's basically n calls. And besides the recursive calls, there's nothing weird going on in this function, right? This is just checking if n equals 0 and then doing one multiplication. So that only takes constant time. So really it's just how many of these recursive calls that you make that determines it. And so all 3 of these things run in O of n time. Now, okay, so what are the differences? For what values of n do they work? Okay, so this one, you say n has to be something like less than 998. If it's bigger, you'll get a stack overflow. Any other bounds on n?
It can't be less than 0.
So if n is less than 0, then this thing will just start counting backwards down to minus infinity, and it'll crash at minus 998 or after 998 steps. So we need n to be in that range for this function to work, between 0 and not more than 998. How about this one? In fact, does this one work at all?
Times equals 5.
Yeah, so there's a mistake in this function. So if we set c equals 1, then at least it will work. And for what values of n will it work? Yeah. So for n 0 should be fine. Even n less than 0, it's not clear what will happen, but n0 seems fine, and so it works for n bigger than or equal to 0. Any upper bound on n? Yeah. Actually, in Python, it doesn't matter. That's a Java issue. In Python, the integers that you have will just get big enough to not overflow. So this works for any n. There's no upper bound, and it works starting at 0. And what about this one? Well, does this work for n equals 0? So think about what the reduce function has to do. It's supposed to take the first element of the array and then apply this function. In this case, it's multiplication with the second element of the array, and then apply that with the third, and then apply that with the fourth, and apply that with so on, until it's done them all together like this. Now, what's it going to do with an empty array? There's nothing it can do. There's no reasonable return value for an empty array. And indeed, if we say reduce lambda x times y, and we do that for, let's say, an empty array, it says there's an error, you gave me an empty sequence, and I don't know how to find any reasonable value for that. But it will happily reduce an array of length 1. Just returns the first value in the array. Okay. So for this one, n has to be bigger than 0. What does this function return? Yep. Yes, I think so. Yep. So this function here. So the first thing when you see a question like what does this function return, first thing you should ask yourself is what kind of thing does it return, and then you can work out the details of what that thing is. So what kind of thing does this return? When I do a list comprehension, what do I get? A list. So this thing returns a list or array, whatever you want to call it. So that's the first thing, is to notice that it returns a list. And what's in that list? Well, so let's see what it does. It's going to make a list that contains this thing. So this is some function of x here for every x that's in the original list. So what is this thing that I've highlighted? So what is this thing? What does an expression like this look like? What does it evaluate to?
Sub the value
Yes. But subs it in and then gives you back what? The string. Okay.
So it'll be a list of strings,
So this will be a list of strings.
which converts all of A into a list of strings.
It converts everything in A into a list of strings. And the format that it uses is the representation format, so it actually shows it to you in something that looks like Python code. So, so the strings are little bits of Python code that make those objects. Okay, so short answer is a list of strings. Okay, here's another function. Looks a little bit like the previous one, but it's even simpler. And what happens if I call it like this? I give it one argument, and that argument is a string. What's that? Yeah, so it goes through each element of the string, each letter of the string, and does what? Yeah. So it will turn this thing into a list that contains all the individual characters of this string. So we can check that out. We say C for C in. You get a list of characters, so strings of length 1. Okay. What about if I do it this way?
Okay, each individual letter. But if it occurs twice, it erases one. Or do you deal with letters?
Yeah, I'll get exactly the same characters, but now they'll be sorted in alphabetical order. So,
Well, like, since it's hurricane, there's no double H if they add words.
what do you mean?
Here I am, rock me like a hurricane.
Yeah, rock you like a hurricane. So what do you think is going to happen?
So like the H in here and the H in hurricane will be like.
No. So if you sort a list, it keeps duplicates. So there's no. We can just check that again. For example, this has 2 A's in it. So if I sort that, well, there's a whole bunch of spaces. Those actually come before anything else. And then these come, and then the 2 A's in a row, the 2 E's, and so on. Okay. Here's a function. So what does it look like this function does?
It returns the remainder of whatever number divided by 10.
Yeah. So, and it doesn't return it as an integer. It returns it as a string, right?
Isn't it like if I put in 10, it's going to give me 1?
If you put in, yeah, you're right, actually. For this to work properly, it should have a 0 there. So one thing to look out for is all of these were made up without much testing. So if you see a syntax error, then it's probably just because it wasn't tested. It wasn't intended. Okay, so now it returns the last digit of whatever number you gave, the last decimal digit, and expressed as a string. And what if I give it something that's not an integer, like math.py? Will it crash? Well, so what is pi mod 10? 3. It's
3.1414.
yeah, it's just pi, because if I try and divide pi by 10, pi is not bigger than 10, so it's all remainder. So all I'm left with is pi. And what happens if I convert pi to an int? Then it truncates it, and it'll give you the integer 3. So this is a safe thing to do. If I neglected this int here, then that would give an error, because I would be trying to index an array with the index 3.14519.
Does that ever actually happen? Could we make an array with like a slot called 0.5?
You can't make an array like that, but you can make a dictionary like that. So, but you'd want to be really careful with that, because we'll see if it works or not, but we could try something like, let's say x equals 0.5, x equals x divided by 3, x equals x times 3. What's the value of x? 0.5. Do you think the key x is in the dictionary? I really don't know. It is, but that was just lucky. So when you do floating point arithmetic, you can sometimes lose precision, and so when you take x and divide it by 3 and then multiply it by 3, you may not get exactly the same number you started with, in which case this would not have found it in the dictionary. And you can't always tell that just by looking at it, because by default it might print a number which is really 0.50000000001 as just a 0.5. Okay. Here's an interesting piece of code. What does it do? Yeah. It prints that one number is greater than another one? Greater than or equal to. Okay. And is it correct?
Does the string won't say it's true? That's one thing. What about the second statement? Does the second statement say, like the second set of square brackets?
Yeah, so this is interesting, right? So this set of square brackets here, what is that thing? It's strings contained in a list. So it's a list with 2 strings in it. So if I take a list and then I put some square brackets after the list, that means I'm indexing it, right? So this is like saying, A equals this. And now what I'm looking at is A at x less than y. So, yeah, so x less than y is either true or it's false. If it's true, that's like a 1, and if it's false, that's like a 0. And so this is really like it will return one of these 2 strings, either the one at position 0 or the one at position 1. Okay. So this thing here is now a string. And you take this string, so this is like, you know, now you've got this string that you just made. It's either this string or it's this string. And now you apply the mod operator, so that's the printf operator, and you give it these two arguments x and y. So those will fill in these two values here, or these two values here. So sometimes you will see this as I've seen this as, you know, a way of doing one-line assignment, basically dodging if statements by doing a one-line thing. It's not, may or may not be something you want to do, but if you encounter it in code, you want to know what it does. This is basically the equivalent of, you know, if x is less than y, return percentage f less than percentage f percentage xy, else return so that's the short version of this longer if statement here. Okay. And you can see what happens. You can call it with different numerical values. You can also call it with strings and see what happens. Okay, here's some lines of code. And work through A. So I want to keep track of what's in A at each time one of these lines of code executes. So A starts out, and this is what's in A. So A is a reference to an array that contains 3 values: apple, orange, and banana. Now I assign B to this funny slice of A here. So what does that do to A? Nothing. So it makes a copy of A, but has no effect on A. So elsewhere there's this copy of A living somewhere else, and B is referring to that copy of A. So when I change B at 1, what does that do to A? Nothing, because B refers to a different array. So no problems there. Now I set C equal to A. So that doesn't change A, but it does mean there is this variable C which now refers to A. So now I set C equal to 1, 2, 3. What does that do to A? Now we have some discussion. Does it? So what does this assignment operator do? Yeah. Yeah. So the picture we've had looks like this. We have this variable called A that refers to this array which contains these 3 strings. I forget what they were. Banana. So A refers to that thing. C refers to that thing when we say C equals A. And next we say C equals 1, 2, 3. So that just says there's an array 1, 2, 3, and now C, instead of pointing to that, will point to 1, 2, 3.
The only time at 11 fact days, like before we made it C1, 2, 3.
Yeah.
We did C1 equals and then a different group. Or would that?
Yes.
Okay.
Yeah.
And then that would change both A and C.
Yeah. So, okay, so let's see. So your question is, we say C equals A, and then we say A equals 1, 2, 3. What happens to C? So we go back to this picture. We were back at that phase. A and C refer to the same thing. And then we say A equals 1, 2, 3. Well, now exactly the same thing happens, except it's A that gets modified. So we create this array 1, 2, 3. And we set A to refer to 1, 2, 3. C is still pointing to this apple, orange, banana thing. Okay. All right, and so now what happens if I set C at 1 to strawberry? Nothing happens to A. Because C is pointing to this different array which contains a 1, a 2, and a 3. So nothing happens there. Nothing happens there. Now I set D equal to A. And then I set D at 1 equal to blueberry. So what happens? Yeah. So now finally we do something that changes A. Well, let's see. Let's be careful. So now I say D at 1 equals D at 2. So now D and A are still referring to the same thing, so whatever I do to D is also going to affect A. And so D at 2 is on the right-hand side, that's banana, and D at 1 is on the left-hand side, that's this index here, so this changes to banana. And now what if I say D equals D at 1? Doesn't change A at all. D now just refers to a string instead of an array. So for these kinds of questions, keep these little boxes in mind, and just remember that this assignment operator, all it does is change what that value in that box refers to. It doesn't do anything fancier than that. Okay. This class hierarchy question I'm not going to bother with right now because it's too big to fit on the screen. It's the kind of thing you need to go back and look at all at once. You know, you create 3 objects, and there's some of them have equals defined, some of them have string defined. What happens if you do different combinations of checking if they're equal or identical? Here are 3 implementations of something that 4 implementations of something that you wrote on an assignment that's supposed to somehow return a list of all the elements in A when their negation is also in A. So if let's say A is a list of length n, what's the running time, for example, of this? So this is a list comprehension that goes over the elements in A. So it'll take on the value of every x in A, and it's going to check if minus x is in A. And checking if a particular value is in a list means you go through the whole list. So this means n times it's going to do this other check, which requires n steps. So it's going to take n squared. This one makes a set out of A first, and then it iterates over A, and then it checks if the negation of the element it's looking at is in the set. How long does that take? Yeah. So checking if something is in a set only takes constant time, and so really all you're doing is iterating over a list of length n and doing a constant amount of work per iteration, so you get O of n time. The difference is whether you're doing a constant amount of work or n work per iteration. Now what about this one? It also creates a set, but it iterates over, so it iterates over the elements of the set, and then it checks if minus x is in A. So this is going to be, in the worst case, it's going to be n squared. The only reason it might be a little bit faster is if, for example, there's not very many different elements in A. Like if there was only 2 different values in A, then this set S would be small. You would just iterate, you would do this twice, and each of those 2 times you would look through all of A to see if this thing was in there. But in general, if everything in A is different, then this is going to still take n squared. And here's one that converts it to a set, iterates over the set, and uses it to check if it's in the set. So this is not any slower than this one up here. It may be faster if there's a lot of duplicate elements in A. But converting to a set takes O of n time anyway. So taking an array A and turning it into a set means you have to look at all the elements of A and put them in a set. So that takes O of n time, so you'll never, even if this step is faster, it's not really helpful. Okay, so tell me the running times of each of these little blocks of code. And you can assume x and y are integers, and A is an array of length n. So x plus y squared, how long does that take? That takes constant time. And how do we write constant time in big O notation? O of 1. Appending an element to the list A. Yeah. It takes constant time. So adding one element at the end of a list, that only takes constant time. What if I do something like this and say B equals this thing times n? Yeah. So what is this? What does this give you? Yeah. So this gives you an array, right? This is a list or array times an integer. So this gives you a list of length n that contains all ones. And so this is O of n. What about something like this? I say B is equal to the full slice of A that contains everything in A. Yeah, so that really means B, you copy, make a copy of A, so everything in A gets copied into another array, and B gets that thing. So that's an O of n. What about if I make B be a copy of the first n over 2 elements in A? Still O of n. It takes half the time, but still It's just some constant times n. It's just that constant is half as big as it was before. If you say, so this is correct, but if you work with an algorithms person and you write something like this, they'll laugh at you. So yes, yeah, you're wasting time writing it down. No, but what's that? O of n. Yeah. Well, you won't get to write anything except little. So you'll lose a lot of marks if you write O of n because it's a multiple choice exam. So don't do that. But yeah, so you don't have to worry about that kind of stuff. Here's a list comprehension over A. Yeah. So in general, a list comprehension takes O of n times whatever you're doing at each step. Well, this is just returning the value that you're looking at. That doesn't cost anything. And then there's an if statement that checks if it's bigger than 0. That takes constant time. So that's O of n. What about this thing? So here's a block of code. It sets I equal to n. While I is bigger than or equal to 1, it divides I by 2. Does that sound familiar? Yeah. So that's our working definition of log n, right? How many times can I divide n by 2 until the result is less than or equal to 1? So that's exactly what we're doing. Here's the same thing, except now at each step I'm doing a list comprehension over A. So this list comprehension takes O of n time, and from the previous exercise we saw that this loop executes O of log n times, so this is n times log n. Out of curiosity, does anybody know roughly what this is doing? So it squares all the elements in A at each step, and it does log n steps. And so if n happens to be a power of 2, then this actually computes each element of A to the power of n. Not critical. If you iterate over A with a for loop and do something in each iteration of the loop, then that's O of n. How about here? Also O of n. That's just a simple check. And what about here? This is O of n squared because you're using this in thing to check if some value is in A, and that takes linear time, or O of n time, and you're doing that n times. This is basically the version, this list comprehension, the slow negated function that we looked at above. How about this? Oh yeah, this should be squared. Sorry. How about this block of code? So this executes n times. Each time it executes, this executes, which is n times, and then this is just a simple thing. So we're looking at O of n squared. Here's a slight variant of that. How many times does this loop execute? N times. this loop, it depends on the value of I, but the best way to think of it, because this starts with j counting at I plus 1 and goes up to the end, but the best way to think of it is, well, on average it's going to execute about half of n times, because sometimes it's going to execute when I equals 0, in which case it'll actually execute n times. Other times, and there's going to be another time when it executes and I is equal to the length of a minus 1, in which case it'll execute 0 times, and then once it'll execute with I equals 1, once when it's n minus 2, and so on. So on those things, if you average them out, give you that on average this executes n over 2 times. So this is you know, about twice as fast as the previous one, but you know, that's just a factor of 0.5. Still in O of n squared. And how about this triple loop here? This is O of n cubed. Good, so you're you're good at answering those things. How about this? This is actually not an easy one. So maybe we could figure out an easier thing is to ask, well, how many times will this line of code execute? Yeah. Well, this line of code should execute log n times, right? Because we start with the length of a equal n. Each time we go through here, we make a half as long as it used to be. And so after log n steps, the length of a will be less than or equal to 1. So this executes log n times, but it also takes a big slice of this array A. So what do you think the running time is? So this looks like n log n. And if you say the running time of this is not more than n log n, then that's fine. But actually it's faster than that. Because if you look at what this does, and this is advanced stuff now, but look at what happens here. First time through this loop, we make a slice of A of half the elements of A. How many elements is that? N over 2. The second time through the loop, A is now half the length. It's only of length n over 2. And we make a slice with half the elements of A. How many elements is that? N over 4. And how about the next time we go through the loop? N over 8. And the next time. And then this goes on until we get down to 1 element. And so another way to write this is to say that this is n times a half plus a quarter plus an eighth plus a 16th plus, and so on, plus 1. Now, have any of you ever heard of Zeno's paradox? Yeah. Just a guy. No turtle. Yeah. Well, the version I know of is just one runner. He's running a marathon, and what Zeno says is, well, if he wants to complete a marathon, the first thing he has to do is complete a half marathon. And then he's still left with half a marathon to complete. And so to do that half marathon, he then has to start by doing a quarter marathon. And then he's still left with a quarter marathon to complete. And that to do that quarter marathon, he has to do an eighth marathon. And then he's still left with an eighth marathon to complete. And so what confused Zeno, although he wasn't really confused about this, but it's sort of a mind bender for his students, was, well, how do you ever finish this thing? This just goes on forever, so you can never finish the marathon. Now, there's problems with that reasoning, because the thing that that neglects is that, well, you can complete a half marathon in half the time it takes you to do a full marathon, and so everything cancels out there. But the point of the sequence is that if I add up a half plus a quarter plus an eighth plus a 16th and so on, there'll always be a little bit further to get before I get to 1. And so this whole sequence here adds up to n times something which is actually less than 1, a little bit less than 1. In fact, it's 1 minus 1 over n, but that doesn't matter. So the point is, this whole thing, so n log n is an easy upper bound, but actually it's really only O of n. And there's a lot of very clever algorithms based on this fact, that if you can make the problem half as big pretty quickly, then you can get a linear time algorithm. Okay, here's a version of binary search we wrote in class. How fast does it run? This was our first try. So O of n log n, and the problem is this stupid slice that we do here, where we slice half the array before we recurse, and that means already then we've looked at half the array. So we're not going to get a running time like log n when we're already looking at n over 2 elements in the first step. But so n log n is an upper bound because each iteration does this slice, which takes at most O of n, and there's only log n iterations because it gets smaller by a factor of 2 every time. But from the exercise we just did, could you tighten that upper bound? So the first time we call this on an array of length n, we take a slice of n over 2 elements, and then we recurse on that. So how big is this next slice going to be that we take? N over 4. And then we recurse on that. How big is the next slice going to be? N over 8, you know, and then n over 16 and n over 32. So actually, the running time is O of n, and that's just from the previous exercise. And what's the recursion depth? Yeah, that's only O of log n. The problem wasn't the recursion depth, it was those slices make things slow. And there's our second version of binary search, the recursive version of binary search. Quite a bit harder to follow because it's got this helper function that takes extra indices. But the point is, if you look at all of these lines of code here, each one of them only takes constant time to execute. And so really you just want to know how big is the recursion depth. It's only O of log n. And each recursive call only takes constant time now, so you get O of log n for the running time as well. Okay. I'll ask one of these at random. So let's say you have an array A. It contains numbers, and it's unsorted. And we would like to determine for everything that's in A, for every item that's in A, the next biggest item. So for example, if the array contains, let's you know, if it was in sorted order, and I say it contains the elements 1, 2, 3, 4, 5. If I take x, well, then I would like to know, for example, what comes after 1 is 2, what comes after 2 is 3, what comes after 4 is 5, and so on. So how would you do that? Well, what would you do before the for loop? So is this something that you could solve with a set, for example? Yeah.
I'm just wondering, couldn't we just find whatever the smallest value is in A, and then that would be the answer for all of them? Except, but even for X, unless it's like smaller or equal.
No, you want the smallest value that's greater than x. So, and you want this for every x, which basically means if you sorted them, you want for every number what comes next in sorted order. So, how would you solve that? Can you solve it with just a set, or do you need to do a little more than that? So I know what I would do. I would make a set to get rid of all of the duplicates, and then turn that into a list and sort it. So now what you get is a list with no duplicates, and if I want to know what comes after any value, it's the next element in that sorted list. What if you had something like this? I give you an unsorted array, and I ask you for every element in that array, tell me if 2 times, so for every element x in that array, tell me if 2 times x is in the array. Yeah.
Why don't we just sort it? Why do we have to remove all the same values?
Well, it depends exactly on the format that you want, but you know, if you have a bunch of 3s, let's say, in there, and you look at the sorted order, well, if you want to know what comes after 3, you'll have to look at a bunch of 3s. I mean, you'll see 3, 3, 3, 3, 3, 3, 3. Oh, finally, it's 3.5 that comes next, or something. It depends exactly. This question is not fully specified exactly what you want, but so you can skip the unique step if you want. How about this one, where you want to know for every x in the array if 2 times x is also in the array? Yep. Yeah. Yeah. So this one fits the pattern of our negated function. By looking at an element, I can tell you what its match should be, and I just want to see if it's in there. So put everything in a set, and then when I'm looking at x, I just compute 2 times x and see if it's in the set. What if I wanted to know the element that appears most often? Which of these techniques would be the fastest? Sorting, binary search, a set, or a dictionary? A dictionary. So we've done this at least once, I think maybe even twice, maybe even in 2 different languages. You create a dictionary where the keys are the values that occur in A, and they map onto the number of times they appear in A. And you can create that dictionary with one loop through the array A. Okay. Here's a little line of code. Should keep that there. So if A is an array of length n, how many times exactly does this line execute? n squared. Exactly n squared, right? Because this executes n times, and every time this executes, it executes n times. So the answer here is n squared. What about this? So this is a for loop. I ranges over the length of A, so this executes n times. This executes sometimes that depends on I. And so how many times does this execute, roughly? So this one here we determined was exactly n squared. For this one, if you had to guess, very roughly n squared. Yeah. So roughly n squared over 2. And actually, it's exactly n times I think it's exactly n times n minus 1 over 2. This I can show you in 2 seconds. This is something Gauss, the famous mathematician, apparently did when he was 9 years old. So really what this question is asking is, what's 1 plus 2 plus 3 plus 4 plus 5 up to, in our case it's n minus 1. You add all those numbers up, what value do you get? Well, you can solve this by drawing a little picture that has 1 block, 2 blocks, 3 blocks, and so on, until the last one has n minus 1 blocks. This is also n minus 1, 2, 3, 4, 5. And remember, what we're trying to do is add up all these numbers, 1 to n minus 1. So instead, you do it by counting these blocks. So what Gauss noticed is, if you take these blocks and take an extra copy of them. So take this picture and make a copy of it, and now turn it around 180 degrees. So you get a picture like this. So the bottom row in this picture becomes the top row in your new picture. And the two pictures fit together really nicely. Like this. My drawing is not very good, but they fit together really nicely like this to make a nice rectangle. So how big is this rectangle? Well, it's n minus 1 on this side, and it's n on this side. So how many squares are there in this picture if I count the black ones and the red ones? It's just n times n minus 1. That's the number of squares. But I'm not interested in counting both the red ones and the black ones. I'm only interested in counting the black ones. That was the whole point of drawing those black squares, is so that I could count them. So how many black ones are there? Yeah. Same number as the red ones, because they're the same. Together they're n times n minus 1, and half of them are black, so that's the number. So n times n minus 1 over 2. So apparently Gauss did that when he was 9 years old, and it took him a few seconds to discover the formula and evaluate it for n equals 100. It saved him the work of adding up all of those numbers. Okay. So just a very quick example. Here's that'll allow you to solve a bunch of these kinds of questions. Here's a function. It's recursive. The base case is when the length of A equals 1, and the usual case, it divides A into 2 parts and recurses on them. And it says, the question says, draw the recursion tree when the length of A is 8. So at the root of the recursion tree, we have an array with 8 elements. And that recursively calls one function on an array with 4 elements, and then, so the first half, and then also recursively calls it on the second half. This recursively calls it on the first half, the second half, first half, second half, and at the arrays of length 1 we stop. Okay, so what's the recursive depth of this function? What's the biggest stack that this function needs? Yeah, it needs room for this frame, this frame, this frame, and this frame, for example, or any of these root paths from the top to one of these bottom things. Now, what's the running time of this function? So if we look at it, it takes constant time, and then it takes a slice of the first half and a slice of the second half. So for example, at the top here, it takes a slice of the first half, which is 4 elements, and a slice of the second half, which is 4 elements. So in total, it slices 8 elements. And here, at this node, it takes a slice of the first and a slice of the second, so it also does it slices a total of 4 elements. Here it slices a total of 4 elements. In fact, at each node, it slices the value that's at that node, the length of the array. Now, if I add all of those up, I get the same number at every level, 8. Okay. So, you know, how long does this take to run? Well, it takes something like 8 plus 8 plus 8 plus 8. So now, if we want to analyze this for a general value of n, we draw this big recursion tree for some unknown, you know, but big value of n. So what's the height of that tree going to be? So the height's going to be log n. And when I add up across these levels, what am I going to get? What value am I getting? N. So all of these 8s, they're really stand-ins for n. So the running time of this algorithm is actually O of n log n. So I want you to go and do these exercises before the exam. Those, in particular, these ones that ask you to draw a recursion tree, because I'm telling you there's things on the exam that can be answered just by drawing one of these trees and studying these kinds of questions like how much work gets done at each node and how do I add that up. So I'll see you in a couple of weeks. Good luck with your studying and good luck on the exam.
That's so funny.